Let's go back to this theorem, 14.5, continued. So let's go over the theorem again. It says if f is differentiable at a point and the gradient is non-zero. I was messing that up, wasn't I? So the gradient is not equal 0. Then the gradient of f is normal to the level curve through that point. So we need to, so level curves are when you set your function equal to a constant. So when f of x, y is z, you get the surface, right? You get the surface up here, you get a paraboloid or something. The level curves are like those curves up on the surface. And then if you project them down, you get those concentric circles, okay? That's what the level curves are. So picture these as all those level curves, different values of k, and how I drew it there. I'm going to use c in the proof. So those are all the different values of k give you those contour lines in the xy plane. So then what we're going to define is this. So I'll keep the picture there as I write this up. So here's the proof. Assume f of xy is differentiable and constant along a smooth curve, period. Okay, then we're going to let r of t basically equal that curve. That's going to be so r of t is going to be g of t, h of t, and we'll just call that xy. So that is a level curve of f. Okay, so basically we're saying, I'm just saying it exists, right? So if this is my level curve, then I can trace it out by that r of t. So I'm just defining what that r of t would be. Okay, so the curve exists in the xy plane, so then we'll just call it that. Basically defining notation. Okay, then if f is constant, we say f of xy equals c, a constant. Or we can put in how the f of xy is defined. So it's that level curve with g of t and h of t. Or we say f of g of t, h of t. So it's just showing like a way to define the function equals c using our old notation of r of t, the vector valued function. Okay, so now this is what we're going to work with here. The f of g of t, h of t equals c. So now differentiate both sides. Remember we were doing that before? So differentiate both sides with respect to t. So d dt of f of g of t, h of t equal to d dt of the constant, which of course is 0. So when I do that, I might, so x is g of t, y is h of t. So I can write it like this. So what's going to happen here? What do you have to do? Oops. what do you have to do to that? F is a function of g and h, and then those are each functions of t. So in that notation, I get you got to use a chain rule. That's what I was basically hoping you would say. You got to use chain rule. So you get partial of f with respect to x. You could say g there, but normally you say x is a function of t. So let's just say that. So let x equal g of t and y equal h of t. All right, so you get partial f with respect to x. Wait, I totally messed it up. I'm too far. That's factoring it. So that means I get if and only if partial of f with respect to x, and then it's dx dt, right? Just like we had, and then partial f with respect to y, and then dy dt equals 0. And then that is a dot product, basically. So if you unpack that, you get partial f respect to x, comma, partial f respect to y, dot dx dt and dy dt, which is r prime. So this is equal to the gradient of f of xy dot r prime of t, which is equal to 0. So that means it's perpendicular. So therefore, the gradient of f is normal to the tangent vector r prime. Which, that's what that means then. Basically, you have all these tangent vectors, like here and here, or anywhere. What you're getting then is your gradient. So this is the gradient, the one in green here. This gradient, that shouldn't be z. Let's get rid of that z. Okay, so that's your gradient of f. Goes like this, and it's perpendicular to all these tangent lines, wherever they may be. So you have a tangent line, and then that gradient is perpendicular. All right, so let's change that color back. So gradient of f is normal to the curve C. To all those contours. So picture a contour graph, right? So picture like a mountain. So you have a mountain, you'll see this sort of thing on a topological map. Okay, and so just make it look one more. So you know, those of you who've seen topological maps, the steepest is when those lines get closer and closer together. Let's put in another one here like this. And then this one further out. I'm going to erase that one. Then the gradient is pointing towards the steepest incline. Well, that's going to be basically perpendicular to those level curves. So that would be your gradient. Then over here, your gradient would look like this. Right, wherever it may be, it's going to be perpendicular. That's the steepest ascent if this is a topological, contour map. And so we know when you hike or something, you're actually, you often traverse along these lines, and you come back, like this to the top. If you go straight up across them, that's the steepest, or up or down, whichever direction you're going. Okay, let's get rid of that one. The rest of those are fine. Okay, so that's the idea of that proof. So important concept, and check out how much stuff we used here. We used now I'm drawing a blank. It's getting late for me here. We used the chain rule with one independent variable to do that. A lot of this stuff is in the setup. I mean, you got to set it up, and we're using the old concepts to combine it with the new stuff and matching it together. Okay, that'll do it for that section.